Almost every safe AI you use today was made safe the same way. Train a powerful model on raw internet text, then bolt on a layer of alignment at the end to make it behave. This paper from Carnegie Mellon argues that's backwards. What if instead, we baked safety into the model from the very first step of pretraining? The usual approach is post-hoc alignment, methods like RLHF applied after pretraining. The authors call it brittle. Once a model has internalized unsafe patterns during pretraining, alignment only papers over them, and a little adversarial pressure or even harmless fine-tuning can peel that layer right back off. As they put it, alignment is not unlearning. So their proposal is to move safety upstream into the pretraining data itself. If the model never learns unsafe behavior as a default in the first place, you don't have to fight to remove it later. They turn this into a concrete, data-centric recipe with 4 ingredients. Here's the whole pipeline at a glance. 4 data interventions feed into pretraining. Filter the data for safety, rephrase unsafe content instead of deleting it, teach the model to refuse, and tag harmful passages with a special marker. The payoff on the right. A model that's natively far less harmful and stays that way even after fine-tuning. Let's walk the recipe. First, safety filtering. Score every document for how harmful it is. Second, synthetic recontextualization. Rewrite risky text into something educational. Third, native refusal. Generate examples of the model responsibly saying no. Fourth, harmfulness tagging. Flag unsafe passages so the model learns to recognize them. Step 1 in detail. They have GPT-4o mini-rate web documents on a safety scale from 0 to 5, with a short justification. Then they train a fast, lightweight classifier to imitate those scores across the whole pretraining corpus. They even propose data safety report cards, a standard way to publish how harmful any dataset is. Step 2 is the clever one. Instead of deleting unsafe content, which throws away real information, they rephrase it. A passage about a historical atrocity becomes a careful, contextualized explanation, even a parent explaining it to a child. This produces SafeWeb, a 100 billion token corpus where the knowledge survives but the harm is diffused. Step 3 handles the genuinely toxic content, the stuff you can't just rephrase. For that, they build RefusWeb. Turn the worst documents into dialogues where an assistant politely but firmly refuses and explains why. They go further with moral education data, reframing harmful topics into articles about the ethics behind them, so the model learns not just to refuse, but to understand why. Step 4 adds a control knob. During pretraining, they insert a special token, potentially unsafe content, into about 5% of the unsafe passages. The model learns to associate that tag with danger. Then at generation time, SafeBeam search looks 1 token ahead, throws out the paths most likely to produce that tag, and steers the model toward safe continuations. So does it work? Dramatically. On standard safety benchmarks, the attack success rate, how often the model can be coaxed into harmful output, drops from 39% for a standard model to just over 8%. That's roughly a 4-fold reduction, just from how the model was pretrained. But the most interesting finding is this ablation, and it's counterintuitive. Look what happens if you just filter, keeping only the safest documents. Safety gets worse, not better. A model that never sees unsafe patterns never learns how to handle them. Removing risk is not the same as building robustness. Watch each ingredient pull the number down. Raw data sits at 39. Filtering to only safe data makes it worse, 44. But add rephrased content, and it drops to 34. Add refusals, 25. Add moral education, 23. And finally, SafeBeam steering brings it down to 8. Every piece earns its place. This figure shows why pretraining beats patching. After light, harmless fine-tuning on math problems, nothing adversarial, a standard model's safety nearly collapses. Its attack rate quadruples. A safety pretrained model barely budges. Because the safety is woven into the weights, not taped on at the end, it survives. And the natural worry, does all this safety make the model dumber? Remarkably, no. Because they rephrase rather than delete, the model keeps the underlying knowledge. Average accuracy on standard benchmarks is actually a touch higher than the standard model. Safety here is essentially free. So the big lessons. Safety can, and maybe should, start at pretraining, not after. Don't just delete unsafe data, recontextualize it, refuse it, and tag it. Filtering alone backfires. Built-in safety, is far more robust to fine-tuning than a post-hoc patch, with essentially no cost to capability. That's safety pretraining, a case for building safe AI from the ground up. If this was useful, subscribe, and let me know which paper you want decoded next.